Boom. Welcome back. In this video, we're going to talk about 8.8 again. We're going to go back to chapter 8.8, the chapter on Cauchy-Euler, and we're going to talk about how to find the solution to a Cauchy-Euler type of differential equation when the right-hand side is not just 0, as in the previous example for Cauchy-Euler. You see that the right-hand side was 0, so it's a homogeneous Cauchy-Euler equation. But in this one, we're going to see what happens when we actually have something on the right-hand side that we need to find and figure out. So in this example, then, let's take into consideration the following problem. X squared y double prime minus 4xy prime plus 6y is equal to x to the fourth sine x. Okay? And there are two types of methods that we can solve this problem with. The first one, method 1 that we're going to consider then, is a variation of parameters method. Okay? And how do we do this type of variation of parameters problem? Okay? Well, we first solve for the homogeneous using Cauchy-Euler. Solve for the home. And so x squared y double prime minus 4xy prime plus 6y equals 0. And remember, in Cauchy-Euler, then this becomes r minus 1 minus 4, and then this is just r, and then this is plus 6 is equal 0. So we got r squared minus r minus 4r plus 6 equals 0. R squared minus 5r plus 6 equals 0. And so r minus 2, r minus 3 is going to be what we get. And then that means that y1 will be x squared, and then y2 will be x cubed, right? So our complementary solution looks like c1x squared plus c2x cubed. And of course, that comes from the textbook right here in the textbook. R1's not equal to R2, and so one of them is x to the R1, the other one is x to the R2. Okay, so that's where that's how we solve the homogeneous, if you recall. And now, what is step 2? Well, step 2 then is to use the variation parameters method. However, there's a problem, right? So we want to use step 2 is to use the variation of parameters. Actually, let's use use this type of numbering. Variation of parameters for the particular. Okay, and you'll notice what? You'll notice that our original equation up here was x squared y double prime minus 4xy prime plus 6y equals x to the fourth sine x. What's the problem with that? The problem with that is we need to have x squared. For variation of parameters, we can't have an x squared term out in front. Okay, so instead of just straight up dividing this thing by x squared, we do the following. Okay, so we set up, right. So we have y1 is equal to this, y2 is equal to that, and so then we say y1 u1 plus y2 u2 is equal to, or y1 u1 prime plus y2 u2 prime is equal to 0. Okay, and then y1 u1 prime y1 prime u1 prime plus y2 prime u2 prime is equal to then x to the negative 2 f of x, which is, so I didn't do this step in the variation parameters video. What you just have to consider is that anywhere we have f of x, it just becomes x to the negative 2 f of x. So if we use the integrals, u1 is equal to negative y2 over Wronskian y1, y2, and I've got an f, right? And u2 is equal to u1 f Wronskian of y1, y2. Okay, what happens is that this integral where you see the f, it has to get replaced by x to the negative 2f. So if we solve for u1, then that becomes the negative integral of y2, which I don't remember what y2 was. Oh, it's x cubed. Okay. And then f of x was x to the 4th sine x, but you have to multiply it by x to the negative 2. And then so you also got x to the negative 2 out here. And then now you got to divide by the Wronskian. So let's figure out what the Wronskian is. Wronskian of y1, y2. And this one should be pretty easy because we got x squared, and then a derivative gives me 2x, and then x cubed, and a derivative gives me 3x squared. Okay, and then, so this is 3x to the 4th minus, the determinant of this, minus 2x to the 4th, which is x to the 4th. So the bottom is x to the 4th. All right, so u1 is the negative integral of x to the 4th, cancels out this guy. All right, and then so this is x sine x. All right. Now, what is the negative integral of x sine x? This looks like something you have to integrate by parts. So let's say u equals, what should u equal? U equals sine x. No, u equals x. Du is equal to, actually, I'm going to bring this negative sign in. So du is equal to negative sine x. All right, and why is that? It's because, okay, du, or dv is equal to negative sine x. And that's because then the integral of dv is actually just positive cosine x. And now du is 1. So, right, this is equal to the uv minus v du, okay? And minus the integral of v du, which is the integration by parts. Okay, and then so that's equal to then uv is x cosine x minus the integral of v du. V du is the integral of cosine x. So this is 1 dx. Okay, so that's sine x dx. Alrighty, and so we know what the integral of cosine is. It's sine, so this becomes x cosine x minus sine x is u1. Okie dokes. Now, what is u2? Right? What is u2? U2, then, let's go back up. U2, if my computer will respond. Okay, u2 is equal to the integral of u1, which is, or y1, sorry, that's not u1, y1. So y1 was x squared, so this is x squared times x to the 4th sine x, but remember, now we need to multiply by this negative x to the negative 2 term, and then the Wronskian in the bottom is still x to the 4th. So what happens is that these guys actually cancel, and this actually is just the integral of sine x dx, which is very easy, right? I've been lazy, I dropped a dx, and I dropped a dx here, it's fine. Because this is now just negative cosine x dx, right? So now what do we got? Now we got so we got now so now we got to solve for the particular solution. Yp was u1 y1 plus u2 y2, right? And so then that just becomes x cosine x minus sine x times y1, which is x squared, plus u2, which is negative cosine x times x cubed. And you'll notice that what happens is you get x cubed cosine x minus x squared sine x minus x cubed cosine x. So you get some nice cancellation going, and the particular is just negative x squared sine x. Okay, and then the entire solution, the general solution then is the homogeneous, which is c1 x squared plus c2 x cubed minus the particular x squared sine x. So this is yc, and this is yp. Okay, and that's how you use the variation of parameters method to solve for the particular solution in this case. All right, and that's just method one. So we got a whole other method to cover. And again, if you're confused with this part, the only takeaway that you really need to do is that then for U1 and U2, right? For U1 and U2, you need to just replace f with x to the negative 2f. Again, because you don't want this x squared term in front. Okay? Because you have that x squared term in front, and you need to take that into account. And I forgot to write up here then that y is equal to u1 y1 plus u2 y2, right? Which is the whole thing with variation of parameters, yp. Cool. Alrighty. So remember, variation of parameters, you isolate the particular solution by itself. You solve for the homogeneous, and then you go to the particular solution. So that's all good. Okay, and this wasn't too bad. So this is for this problem, variation parameters would have been perfectly fine, and it's generally one of the better ways to solve it. And let's see if I want to say anything else about this. Not really. Okay, so remember, in variation parameters, you're solving for the particular solution, which is why when we take our integrals down here, there's no constant terms, right? There are no constant terms. When integrating to solve yp, the particular solution, okay? And remember, in the reduction of order video, there was a constant term because reduction of order is different, which is actually method 2 is using reduction of order. Okay. And how do we use reduction of order? Well, remember, we just started off with this. X squared y double prime. Yeah, I don't remember what the thing was. Minus 4xy prime plus 6y. Okay. So minus 4xy prime plus 6y is equal to x to the 4 sine x. Remember, we started off with this. And what is required in reduction of order? Reduction of order, it requires a solution. Right? Reduction of order requires a solution to the differential equation, which is a problem because here it doesn't look like we're given any solutions to the differential equation. But this is where reduction of order is super flexible and super good, is that you can use a solution to the homogeneous as one solution. So step one, again, is to solve for the homogeneous, which again was c1 x squared plus c2 x cubed, right? It's the exact same problem, okay? So that means y1 is equal to x squared and y2 is equal to x cubed. And so for the reduction of order method, then, I can just say, oh, y is equal to u times y1. Right? That's what reduction of order is. My general solution is equal to something times some solution that I already have, which is y1. And so now I can just take this y1 from up here. Right? So now I say, okay, y is equal to actually just u x squared. Okay? And remember, this is really u of x. So u of x times x squared. So y prime is going to be u prime times x squared plus 2x times u, all right, by the product rule. And then y double prime is going to be u double prime x squared plus 2x u prime, all right, and then plus 2x u prime plus 2u, okay? And now what do I do? So this is, remember, you take your derivatives, and now you got to plug it back into the equation. So now you got to plug it back in. This becomes x squared times y double prime. Okay, but what is y double prime? Y double prime is here, and remember, in reduction of order, we can ignore the u term. So this is u double prime x squared plus 4x u prime. Okay, so reduction of order, I can just ignore these u terms, right? And now what? So, okay, so I just erased them, but you erase them after you take your derivatives. Like, don't erase them in the intermediate step, because then you're going to lose some derivatives that you need to take. Okay, cool. So I don't need to erase, I can ignore the one. Whatever. Undo. undo. Redo. Okay, so yeah, we'll just ignore these guys. So just ignore anything with a u in it, right? Because we just want the primes and the double primes. And then this is minus 4xy prime, which is u prime x squared, and then plus 6y, but that doesn't matter. And this is equal to x to the 4th sine x. All right. Now what? Now we got u double prime x to the 4th plus 4x squared u prime minus 4x cubed u prime. Oh, this is actually 4x cubed u prime. Okay, so this works out. Equals x to the 4th sine x. Cool. And so now you got u double prime x to the 4th is equal to x to the 4th sine x, right? Because the middle x cubed terms cancel. And now what? So now you got to solve for what u is. So now you got u double prime is equal to sine x. And this actually isn't bad because now we just start integrating upwards. And so u prime is equal to the integral of both sides. So it's equal to negative cosine x plus some constant c1. All right. And now u double prime is equal to negative sine. We're taking integral. So this is not u double prime, but u. Okay, so now we integrate again. We integrate u prime, and we get negative sine x plus c1x plus another constant, c2. All right, and now we have u. And now, remember that y was equal to u times y1, right up here. Y is equal to u times y1, which is now negative sine x plus c1x plus c2 times x squared, right? So this was u, and this is y1. And look, what do we get? We get negative x squared sine x plus c1x cubed plus c2x squared, which if we compare to the equation up here, right? So we got this equation right. You got this equation right here, and we compare it to this guy down here, you notice that they're the same thing, right? You got the negative x squared sine x's, right? And then you got c1x squared. Well, this is c2x squared, but it's just a constant, right? So it doesn't matter. And then you got c2x cubed, and you got a constant times x cubed. So they're the same way. And these are the two methods you can use to solve your Cauchy Euler with a right-hand side type of problem, variation parameters, where you have to take into account this extra x squared term, and then also the reduction of order method, where you cleverly use a solution to the homogeneous as your y1 guess. And so, which way should you use? There's no correct way. There's no incorrect way. Sometimes reduction of order turns out to be really bad, especially when you have to deal with logarithms, so ln's. And so I would suggest maybe like which one you feel more comfortable with. And most students are going to say variation parameters, which is perfectly fine. It's a perfectly fine method to do this. So the last thing I want to point out is that this reduction of order method, notice how we just solved for a homogeneous, right? We solved for the homogeneous, and we took a solution from the homogeneous, and we used it in the reduction of order. This always works. This always works for every differential equation ever. As long as you can solve the homogeneous, you'll always have a solution to plug into the reduction of order equation. And so this is a nifty tool to, if you run into some differential equation that you can't solve, but for some reason you know how to find the homogeneous, you can just use reduction of order. And yeah, like this is a very good method. Reduction of order is very powerful, but it might be off-putting to some people because you learn it later, and it's perceived as harder than the other methods. So keep that in mind. Reduction of order is very good. Very powerful method to solve differential equations. And that's it. That's it for differential equations. So now we're moving on to systems of differential equations, which doesn't sound too different, but it actually is a little bit different in the sense that's more like chapter 7 rather than chapter 8. So yeah, I'll see you guys in the next video.